Welcome to The Explainer. Today, we're unraveling the fascinating science behind creating and actually controlling an invisible physical force. We're kicking things off right away with some pretty incredible slow-motion footage. Just look at these metal paperclips suddenly jumping right through the air, snapping onto a homemade coil-powered magnet constructed by Dr. Chem. Now, it looks like magic, right? But it's pure physics. So let's break down exactly how this happens. Let's start with a provocative question, one that really bridges the gap between a tiny little spark on a workbench and heavy industrial lifting. Can a simple electrical current create a force strong enough to lift massive metal objects? I mean, it's one thing to see a handful of paperclips snap onto a battery-powered nail in a lab. It's an entirely different thing to imagine that exact same basic principle scaling up to power those massive scrapyard cranes hosting tons of jagged steel. But as you'll see, the underlying mechanics are literally exactly the same. Okay, here's our roadmap for today. We're going to cover what is an electromagnet, building a DIY electromagnet, engineering for maximum strength, the science of cores, and finally, modern industrial applications. Let's dive in.
Section 1. What is an electromagnet? The power of control. So the absolutely crucial point to understand here is that electromagnets give us the ultimate superpower of control. It's the ability to turn a magnetic force on and off completely at will. Now, permanent magnets are made of naturally magnetized materials, meaning their magnetic field is always on. They permanently display magnetic behavior. But electromagnets, they only produce a magnetic field when an electric current is actively flowing through a coil of wire. The very second that flow of current stops, boom, the magnetic field instantly disappears. And this fundamental difference is the silent engine driving everything from your simple doorbell all the way up to heavy manufacturing.
Moving on to Section 2, building a DIY electromagnet, the microscale.
To really grasp the physics here, let's take a look at Dr. Chem's laboratory workbench following some standard guidelines from the University of Wisconsin. In this cinematic time-lapse, you can see the whole construction process. First, tightly wrapping insulated copper wire around an iron bolt to form a coil. Next, connecting the stripped ends to a simple battery. The exact moment that switch is flipped, the bolt becomes completely magnetized. Why? Well, because those flowing electrons actually behave like tiny magnets. Wrapping the wire concentrates them, and, as visualized by those animated blue field lines, it creates a highly powerful unified magnetic force.
Section 3. Engineering for maximum strength. Variables of power. Now, through some pretty exciting comparative lifting experiments, we find that we actually have a few options to scale up that lifting capacity. First up, coils. Doubling the tight wire turns roughly doubles the magnet's strength. It's a nice, linear, highly cost-effective relationship. Second is current. Increasing your input power proportionally increases the magnetic field. But, and this is a big but, we absolutely have to watch the temperature. Higher temperatures increase electrical resistance in the wire, which actually drops the current and weakens the magnet. So packing in more power requires some serious cooling management so we don't literally melt our experiment.
The real secret behind these experiments lies in Ampere's circuital law. This mathematical law is basically the ultimate engineering blueprint. It proves exactly why adding more current or tightly packing more wire turns into your coil multiplies the total magnetic flux. It's the exact calculation an engineer needs to map out and build a vastly stronger magnetic field. But actually scratch the idea of just pumping infinite electricity into a wire to get an infinitely strong magnet. It doesn't work like that. There are extreme physical limits here, and one of the biggest is the Lorentz force. In super powerful electromagnets, the magnetic field exerts this intense outward radial force on the moving charges within the wire itself. This pushes the magnetic field lines apart and causes massive tensile stress. If those windings aren't firmly clamped down, the sheer force of this violent power-up and power-down cycle can cause metal fatigue and literally push the coil apart from the inside out.
Which brings us to Section 4, the science of cores, visualizing the invisible.
Take a close look at this BH curve, which beautifully maps out the behavior of a ferromagnetic core. Now, an air core electromagnet by itself is pretty weak, but inserting an iron core forces billions of tiny internal magnetic domains to align perfectly, amplifying the field thousands of times over. Notice how the graph starts out totally linear, hits that knee, and then just levels off completely at the top right. That flat line is what we call magnetic saturation. It's the exact point where literally every tiny domain is aligned, meaning pumping in more current simply won't make the magnet a single bit stronger.
And this brings up a really critical engineering choice. If we want the absolute strongest, most efficient core, we gotta ask, why do engineers specifically choose soft iron over a much harder material like steel? You'd probably think tough steel makes for a better industrial tool, right? But for an electromagnet, it's actually the exact opposite.
The answer lies in two very specific properties: permeability and retentivity. Soft iron has high permeability, meaning it readily accepts and massively amplifies that magnetic field, but more importantly, it has extremely low retentivity. When you shut off the power, soft iron instantly scrambles its internal magnetic domains and completely loses its magnetism. Steel, on the other hand, stubbornly holds on to its magnetism. It's a phenomenon called hysteresis, which results in remnant magnetism. Just imagine an enormous scrapyard crane using a steel core. It picks up a 2-ton car, swings it over a shredder, the operator cuts the power, and the car just stays perfectly stuck to the crane because the steel core has essentially become a permanent magnet.
No way!
That's exactly why soft iron is absolutely essential. We need the magnet to let go the millisecond we flip the switch.
Section 5. Modern Industrial Applications, the Macro Scale.
From levitating trains to life-saving medical scanners, the ability to concentrate and manipulate these magnetic fields is literally the silent engine of modern industry. Think about it. MRI machines use ultra-powerful electromagnets to peer inside the human body with stunning precision. Maglev trains use electromagnets to actually levitate carriages right above the tracks, giving us frictionless high-speed transportation. We already talked about those massive lifting cranes in scrapyards, but it also scales way back down into the guts of our automated world. Electric motors constantly converting electrical energy into mechanical motion, and tiny electromagnetic solenoids and relays instantly opening and closing industrial valves on automated assembly lines. It's everywhere. I think this quote from Electroflux Equipments beautifully summarizes our entire journey today. Electromagnets only produce a magnetic force while electricity is flowing, meaning operators may turn them on and off, modify their strength, and incorporate them into automated machinery. You see, the true marvel of the electromagnet isn't just its raw, brute strength. It is absolute, precise control. It's the ability to completely command a fundamental force of nature with the simple flick of a switch.
So what should you really take away from this explainer? Well, as you look at the world around you, consider how the simple interplay of some copper wire and a soft iron core might shape the massive innovations of tomorrow. From Dr. Kim's workbench experiment picking up a few paper clips, all the way to floating trains speeding across entire continents, we have truly only scratched the surface. So I'll leave you with this. What impossible engineering feats will we unlock next by mastering the control of this invisible, incredibly scalable force? Thanks for joining me for this explainer, and keep looking for the invisible forces shaping your world.